So, welcome again to this new lecture on solar photovoltaics principles, technologies and materials. We will again look at the p-n junction in light. So, let me just recap the last lecture. In the last lecture we were talking about p-n junction. So, we in the lecture before we did analysis of p-n junction in light, and we got the current expressions for electron current, hole current and the space charge region current, and we looked at the simplifying those equations with making certain assumptions. So, first assumption was that what will happen if you make if you analyze them for p-n junction in dark and without illumination, and that is straightforward. It should take you to p-n junction in equilibrium, which means there is no current flowing. And then we looked at the case of p-n junction in dark without illumination but with applied bias, and then that should take us back to the p-n junction in dark without the bias. However, later we introduced since we introduced space charge region current, which is finite in practical diodes, and as a result of this recombination within space charge region as well as radiative recombination in the semiconductors, we have recombination current from space charge region, and this gives rise to non-ideality in the devices. So, if you recall, we had this curve, we had this expression here. This tells us that dark current is equal to the diffusion current, which we also derived earlier, but in addition now we have added space charge recombination generated current and radiative recombination, and these factors are dominant in practical devices. So, if you have indirect bandgap semiconductor, generally it is observed that radiative recombination is higher and space charge recombination is lower. As a result, indirect bandgap semiconductor, because you have lesser in radiative recombination, and if the diffusion lengths are larger than the junction widths, then as a result, or space charge region width, then your dark current is predominantly diffusion limited. However, for direct bandgap semiconductor, which have high absorption wide space charge region, as a result the carriers do recombine. So, more recombination losses and high radiative recombination in these semiconductors, this gives rise to a dependence of QB by 2 kT, which is observed. And generally what happens is that we see more than one processes. As a result, we have we generalize this equation as J dark V is equal to J naught into exponential QB by m kT minus 1, where m is the ideality factor. So, when m is equal to 1, which means the behavior of device is ideal, but if m is greater than 1, then the device behavior is non-ideal, which means more than one processes are active in terms of dark, as far as dark current is concerned. So, this is what we were doing. So, generally there is a transition from space charge current to diffusion current that happens at very low voltages, but if your carrier lifetimes are smaller, carriers diffuse, they recombine or diffusion lengths are shorter, then the transition to diffusion current is at higher voltages. That is what we saw. And then finally, we were looking at the p-n junction under illumination, where we said that you have a semiconductor device with 0 voltage applied, and there is no net recombination in space charge region. However, you have lot of generation. So, as a result, you have large generation current within the space charge region at 0 bias. So, the total current is now equal to electron current at minus Wp plus hole current at plus Wn plus the generation current. You will have some recombination also, but the generation current dominates over anything else as a result. So, you will have always radiative recombination in the device, but since you do not have any applied bias, there is no space charge limited current here, SCR current. So, this total current is the integration of this spectral current over the whole energy range. What happens here is the quasi Fermi levels for electrons and holes, because of increase in population of electrons on the p side and holes on the n side, the Fermi levels are split, and this change in the Fermi levels on p and n side gives rise to migration of holes from n to p side and p to n side, electrons from p to n side, which is counterintuitive against the p-n junction in dark, and this gives rise to a current which is negative in sign, and that is what you observe at 0 bias, and this is the current which is driven by split changes in the Fermi level, and this Fermi level gradient is the one which drives the electron down to the n side from p side and hole from n side to p side, which is normally not the case in p-n junction in dark. So, now we are going to further analyze this. So, if you look at the further, if you just look at those equations, so the equations in this case, the Jn and Jp equations, you can see the current sign is in negative. You have this Is term, and there are other factors which are with respect to your surface recombination velocity, diffusion lengths, and coefficient of absorption, etc. And the total current now, since we said total current is in negative, right? We said that this current, all these three currents that we look, so we said that J total was equal to Jn E minus Wp plus Jp E Wn plus Jgen. All these three currents are negative. So, the total current of this device is basically the current is negative. So, minus of Jn E minus Wp plus minus of Jp E Wn. So, if you want to just convert, so you need to basically integrate this over the whole energy range, and this should also be integrated over the whole energy range, and the total current which is obtained because of the current which is because of electron hole migration and generation current, this should be, so diffusion current plus generation current, this should give you the ratio of this current with respect to whatever power is incident according to that. So, number of, basically this is the spectral flux or spectral energy. If you multiply this by charge, you will get that many number of carriers that should be created. So, ratio of these two will give you the quantum efficiency of the device. Okay. So, suppose you had 100 photons falling here, 100 photons will give you 100 electrons plus 100 holes, right. What you get here will be some other number, it will be x electrons and some y holes, let us say, right, because of differences in electron and hole current, they are not similar. So, the ratio of current corresponding to this with respect to what should have been ideally created is the quantum efficiency. Okay. So, this is what you have got and this is what you should get ideally, and of course, this number x and y is always going to be smaller than, so sum of this is always going to be smaller than 100 that you get here. So, that is why the quantum efficiency is not 100%, but rather lower. So, you can get quantum efficiency of the order of 80%, 70% or so in semiconductor devices. So, to solve this further, you can approximate, and this approximation is first you can make a long base approximation. Long base approximation means the diode is very thick, the PN junction is extremely thick, and we assume that Xp is greater than XLN and Xn is greater than Lp. In such a case, surface recombination term becomes invalid. As a result, you can modify these expressions as the electron and hole current expressions are modified in this fashion. So, you can see here that the surface recombination terms vanish. So, these two terms become much more simpler, primarily dependent upon the minority carrier lifetimes, absorption coefficient, and the width of junction and width of device. That is the only factor it depends upon. You can also make short base approximation when Lp and Ln are much longer than Xn and Xp. So, you can see that this is the assumption that we make. This is a short base diode. In such a situation, your surface recombination is relevant, but Ln and Lp becomes irrelevant because they are longer than Sn and Sp. As a result, you will see that Ln and Lp disappear. What you have is surface recombination term appearing. So, this is how you simplify the equations that you see in the first slide. I mean, this has both the terms, the recombination term, the surface recombination term, as well as the diffusion length term. So, we make these approximations to calculate these currents with much more simpler. So, this is what the current you will get for without the bias. So, of course, the total current that you will obtain is J total that you will have is, so minus JSC is the one which you obtain from the short circuit, and whatever is J rad, which is the positive current which is going to give rise to. So, so this, or you can, I mean, plus and minus signs will depend upon how you take, but this is the, let us say if you make it this plus, this will be the negative current, this will be the positive current, radiative current, and this radiative current or recombination current or diffusion current, whatever you generate as a function of bias, when you apply bias, this will start countering this current. So, that is why you will see what you get at 0 bias if you plot IV. This is the short circuit current, alright, at 0 bias, and as you keep applying bias, the curve goes like this. This means your ISC is being now countered by IV, which is the diffusion current, which is the space charge recombination current, and if you have any radiative recombination current, that will also contribute, and they are all positive currents. So, all the positive current factors which we saw earlier for p-n junction in dark, they will start opposing this negative contribution. So, and that is obvious from the Fermi level, that is obvious from the this diagram as well. So, this is the p-n junction diagram. So, the negative current is because of, so this is P, this is N. So, negative current is because of movement of, let us say, so we said that movement of holes from this side to that side. Similarly, electrons will move from, so these are the electrons. So, both of these will give rise to JSC, and as you apply bias, what will happen is that as you apply bias, the holes from this side, which are plenty in number, so holes from this side, they will start moving to this side, and electrons from this side, so these two will contribute to IV, and they will start countering your ISC. Okay, is that clear? So, this is what the basically reason behind the shape of the IV curve that you get. Why does the current become 0 at certain points? So, at certain point, which is called as open circuit voltage, the current becomes equal to 0 because IV starts dominating over ISC. Okay. So, this is what we have discussed so far. So, essentially if you have now, if you have a p-n junction, illuminated p-n junction with bias, let us say, so if you have an illuminated p-n junction with bias, let us say we make a plot of energy as a function of distance x. So, let us say this is your EC, okay, and this is your so somewhere here, let us say, okay, so this is your, okay, and this is basically, you can say this is now equal to VBI minus V, because now you have applied bias VA. Okay. So, the Fermi levels will start slowly start shifting down. So, this Fermi level, which is EFN, the quasi Fermi level for electrons, which goes like this, the quasi Fermi level for holes, which is on this side, it goes like this, okay, something like that. So, this is, let us say, EFP. So, normally, see, the beauty of this is, normally you consider for p side the Fermi level corresponding to holes, because p side is a hole rich. You consider a Fermi level for electrons because this side is electron rich, but since because of illumination you have caused sudden flux of carriers, these Fermi levels are also corresponding to electrons and corresponding to holes are very high, and that is what drives down the electron migration and hole migration from this to this side. This is now countered by electron migration from hole migration, electron migration from, so this is from N side. So, this is electron migration and this would be hole as a function of voltage, okay, and this is what will give rise to your decrease in the current. So, current will slowly decrease as V increases until VOC when IV takes over ISC. Okay. So, that is what will happen. So, when the bias induced current, which is the forward current, takes over the diffusion current and space charge current and so on and so forth, when it takes over the short circuit current, that is generated only because of, primarily because of generation. Okay. So, generally what happens in a solar cell device is, so solar cell device, let us say we have a junction like this, assuming that you have a junction in this fashion, so that your sunlight is coming in this fashion from top. Let's make it orange, this is sunlight, and you have a PN junction which is something like this. So, you have a, let us say this is P side, this is N side, this is space charge region, okay, in between. So, first you are going to have absorption in the P layer, then you are going to have absorption in the N layer, in between you are going to have absorption in the space charge layer. So, the quantum efficiencies vary something like that in semiconductors devices. So, if you now plot the quantum efficiency as a function of wavelength, then your basically in the P layer, the so shorter wave, so you will see that the your shorter wavelengths are going to be absorbed in this region. So, in this region you will have short lambda absorption, and this layer you will have long lambda absorption. So, you will see that the absorption, the quantum efficiency for bottom layer is high in this region, the top layer contributes in this region somewhere here, something like that, and a space charge region will contribute somewhere in between. Okay. And the overall quantum efficiency will be, if I now plot the overall, this will be overall quantum efficiency. So, this is QE overall, this is from top, this is from bottom, and this is from space charge region. Since the space charge region is very narrow, that quantum efficiency of this region is also, and also there is a lot of recombination in space charge region. As a result, the quantum efficiency is smaller in case of space charge region, but generally P and N sides have high quantum efficiencies. And high quantum efficiencies generally are obtained when, so high quantum efficiency is obtained when you have surface passivation, which means you have low surface recombination, right. This is mainly due to dangling bonds. So, if you reduce the number of dangling bonds on the surface, the carriers will not get recombined at the surface. So, and also reduce the reflection losses, which means the carriers are not the photons are not reflected, all of them are absorbed. And then of course increase the cell width. So, suppose you have I naught here, you do not want anything to come out here. So, if the cell width is larger, then more radiation is absorbed within the solar cell. So, you can put reflectors for another. So, it is not a problem in silicon solar cell, but it could be an issue in the thin film solar cells where the thicknesses are lower. So, basically increase the cell width to improve photon absorption. Okay. And more photons you absorb, better the quantum efficiency. And then of course, you have light trapping to prevent light loss, to prevent photon loss. So, essentially the idea is, suppose you throw 100 photons on top, the idea is to maximize all of those photons in carrier generation and then carrier collection. Okay. So, if you throw 100 photons in, you are likely to create 100 electrons in hole pairs, and device engineer's job and materials engineer's job is to collect all those 100 electrons and 100 holes at the terminals, so that you collect all the carriers. otherwise there will be recombination of carriers, or if you lose photons, of course you are not going to correct, you are not going. So you want to achieve you want to adopt every means to maximize the quantum efficiency, such as by doing surface passivation, so that it doesn't. So even if you absorb, let us say 100 photons, the carriers are going to be recombined at the surface. So you want to passivate the surface to prevent that. You want to reduce the reflection losses so that you capture all the photons. You increase the cell width, so again you capture all the photons as much as possible, and then you do light trapping strategies to prevent the photons from escaping. Okay. So these are the techniques that we generally follow as far as methods of quantum efficiency improvements are concerned. So and there are other factors also which you can consider to improve the current collection, and these other factors are dependent upon, for example, materials quality. So material quality has various connotations to it, we will come to that. So basically what we mean in terms of semiconductors is to materials quality means, so material quality will mean low defect density. Generally if you have higher defect density, you will have more recombination, as a result more current will be, your fill factor, basically these will reduce your fill factor. So if you look at this IV curve, okay, the idea is to get a IV curve which is like this, but if your IV curve happens to be like this, alright, something like that, this means your IV is more dominant than it should be. And remember, IV is made up of what? IV is made up of your diffusion current, space charge current, and radiative recombination current. So which means if your state charge, and this is well visible in the dark data. So if you analyze the dark data very well, you can see which of these factors is dominating, and this is most of the times related to defect density. So if your defect density is lower, then of course your material has so idea is to increase Ln and Lp, they will improve the they will reduce the recombination, and idea is also to reduce the Sn and Sp. Okay. And of course there are other defects in the material, microstructural defects and so on and so forth, they should be reduced in density. And another thing which is quite commonly talked about is in silicon context. In silicon, generally the top layer is called as emitter, we will see this later on, and the bottom layer is called as base, and this top layer is generally P plus, and this is N layer. Oh, sorry, this is N plus and this is P layer, I am sorry. So this top layer is generally, this is Pn plus kind of junction. So emitter is generally made very thin as compared to base, because the carrier recombination is larger in case of because the carrier lifetimes are longer in base, electrons have longer lifetimes in base. As a result, you can make the P thicker as compared to N side. So carriers travel longer distance as it is. So this is something, so effect of basically you can say XP and Sn, because you will have electrons coming on this side. So you are going to look at the electron recombination velocity, surface recombination, and the electron diffusion lengths within the P side. So this is these are important factors as far as silicon semiconductor devices are concerned. So silicon solar cells have these practices which are about making emitter thin and base thicker. There are some things also related to, let me just show you some data with respect to, so if you look at, for example, quantum efficiency as a function of wavelength. So this is lambda in nanometer. So we are generally plotting from about 400 to, let us say, about 900. So if your XP is thin for a certain case, so let us say in the case where recombination is large, as you increase the thickness. So if your thickness is, so let us say if your Xn or Xp, whichever you may have, if your quantum efficiency is like this, and suppose you start making the layer thicker, thicker layer on one hand lead to improved absorption, they also lead to higher recombination. So, if you increase this x, let us say xp in certain case, then increase in xp can lead to decrease in the quantum efficiency because of increased recombination. This is true for certain cases, it may not be true for all the cases, but for certain cases. And then we have, for example, surface recombination velocity. So, if you plot surface recombination velocity as a function of lambda, so if you have low Sn, then your curve is like this, but if your Sn increases, the curve tends to be like this. So, you can have curves like that. So, again 400 to 900, let us say. So, this is, you can say, increase in, for example, Sn, okay, for a certain semiconductor device. And likewise, you can have effect of, if this is for Sn, you can also for Sp, for the other, this curve may also, depending upon the, so in this case this is the top layer, because you can see that the most of the decrease is happening in the top layer. This is also in the top layer. So, these are both related to top layer. It can also happen in the bottom layer like this. So, if you are in this case, I think it is about when your carrier recombination length, you can say diffusion length, decreasing, okay. So, quantum efficiency decreases, and this is in the top layer region. So, whether it is because of LP or LN or SP or SN, that will depend upon the type of semiconductor device, but you can see in which region the decrease or increase is happening. So, if the decrease is happening on the shorter wavelength side, then it is mainly because of the top layer, and if it is happening in the longer wavelength side, it is happening because of the bottom layer. So, we will stop here today. We will discuss other things about the solar cell operation in the next class, and there are a few more things before we go to discussion of materials and technologies. Thank you.